Uh, Today we're going to see machining of what we call as a Sigma blade. Sigma blade, as most of you might be knowing, is a very popular product, and it's very popular in the process industry where mixing of high viscosity material happens. For example, it could be a pharmaceutical industry, it could be rubber, it could be chemical industry. So wherever there's a high viscosity material that need to be mixed, they use the mixers, and inside the mixers you have the Sigma blades. Sigma blades basically have dual action. They mix as well as they shear the material. That's because of the unique profile of the blade. The helix itself is pretty unique, and we're going to see machining of this particular blade using both iMachining 3D and simultaneous 5-axis. Now, there are some preparatory things that we need to do before we start the machining, and there will be a lot of things we will see which are there inside SolidCAM but not been demonstrated, so that also we are going to see today in the webinar. All right, let's start a new milling exercise. Okay. Right, so we're going to use a DMG DMU 100 monoblock machine, with a Heidenhain control. And our coordinate system, the first coordinate system, is going to be the revolution, the center of revolution of this face, whereas my x-axis, or my z, whichever I call it, it's going to be along that edge. But since the DMU 100 monoblock has two variants, it has a c-axis variant and it also has an a-axis variant. We are going to use the a-axis variant, wherein the rotary axis is going to be along x-axis. So we need the axis of the cylinder to be the x-axis. To do that, simple, I'm going to first make my z-axis up and use the z-axis. So I'm going to flip along z and make x-axis go along the center line of the cylinder. So that's my rotary axis. All right, so we have done with our first coordinate system. Let's input some whole numbers. Okay, that's done. Stock, we are going to use a predefined stock already. So I'm going to unselect this and use a 3D model. I already have a turned block. Done that. Target is going to be this particular solid. This is my final target. And as far as my iMachining goes, I'm going to use a DMU 100. I've already defined this machine in my database. I'm going to use a DMU 100 monoblock machine, which has a maximum spindle RPM of 15,000, a maximum cutting feed rate of 12 meters, a repositioning feed rate in Z, I've reduced it to 1200 millimeter per minute, continuous spindle power of 15 kilowatt, and we are going to use a machining level, a default level of level 6. On the material front, these blades are generally made out of stainless steel. So it could be a SS304 or 316, depending on which process it's being used. But for today's demo, we are going to use a 6061 T6 aluminum, just to understand how iMachining also works like. Okay, so we'll pick DMU 100 monoblock from the database and 6061 T6. This is having about 460 megapascals of ultimate tensile strength. Okay, let's accept it. Right, we are now ready for our demonstration. Let's turn the background to plain white. Much more easy to see it. Right. Now, before we begin this machining, I told you that we need to make some preparatory stuff. What are the preparatory stuff that we are going to do? We are going to split few surfaces that's going to enable us to do our 5-axis machining much more easily. Okay, so we're going to go into the part environment and define a plane that's coincident to that face, and then use the split line function of SolidWorks to split these surfaces using that plane. So what I'm basically doing is I'm creating regions for me to machine in 5-axis much more better. So we've done the first region out here. The second region is going to be here. So we'll create another plane coincident, and we'll make a split line, all these faces. Okay, this is done. So what we have now is we have one region, we have the second region. Now for the third region here, I would need to create another split line, coincident, and another split line using this face. I'm going to pick all these surfaces. Okay. So what we have now is one region, the second region, and the third region. So this is going to make it much more easier for me to do the 5-axis programming. Since this is a similar blade on either sides, I'm just interested in doing only one side, the other half, although it's going to be very similar, or rather same. Okay, so let's begin. We'll start with iMachining 3D. So I'll add iMachining 3D. Target, Mach 1, position 1. That's my first coordinate system. And I'm going to use a 16 millimeter bull nose. I have an arbor diameter of 15.8. Tool length of 100 out of folder of 75, 45, and 45. So we have a cutting length of 45 millimeter, or I would say just 40 millimeter. And it's a 3-flute tool. Holder, I'm going to use an HSK 32 by 80. That's the standard holder we're going to use for this. And I'm of course going to use the holder collision. This is a nice option inside iMachining 3D, wherein the system checks for collision between the holder body and the stock or the part. And the clearance that I'm going to use today is about 10 millimeter. In the levels, my upper level is going to be 80 because the stock diameter is 160. So my upper level exactly is half, 80. Lower level, I'm going to keep exactly the same one because this represents a level somewhere here. This is the level it represents, so I want to machine that entire thing out here. Okay. Let's go to the technology wizard. If I go to the modify cutting conditions, I realize that I'm using only 7.1 kilowatt of the power available. That's about 50%. I want to go up to about 9 or 10 kilowatt of the spindle power. So that will mean that I'm using the optimum power from the spindle. I'm neither underutilizing it nor I want to overutilize. So I'm going to push the turbo mode. The moment I push turbo on level 6, it tells me that I'm going to use about 15 kilowatts. That's 100% of the power that's available. I can do two things here to reduce the power. I can cut down on the engagement angle. That still doesn't bring it to less than 15, so I'm going to cut it down to further, let's say 40. You can see that the engagement angle comes down. But here, I'm going to use a combination. I'm going to keep the engagement angle as 50 degree, but I'm going to get down the chip thickness to about 0.15, which in the combination will give me a power of about 10.9 max that will be consumed by this spindle while cutting this part. Okay. Let's go to the technology. I'm going to keep a stock of about 0.8, and the toolpath parameter is about 50, the tolerance is about 50 microns. Right, and in the max arc size, I'll bring it to close to about 8, somewhere in the range of 8 millimeter. Z clearance, it's going to lift 0.15 every time. Right, so we have done this. I'm going to save this. Okay, there is a synchronization needed. That's done. Let me copy this because I need to do both the sides, 0 and as well as 180 degrees. So I'm going to copy and paste it, edit, and we're going to have a new coordinate system. So I'm going to add a new coordinate system, origin to be at the coordinate system number 1. And I'm going to select this face because I want my Z to be normal to this face. So there it is, Z, X, and Y. That's perfect. Okay. 175. Let's just 100 again. Rest everything is fine. Okay. So I'm at Mach 1, position 2. Pick the target. Everything else will remain the same. Of course, here it goes up again to 80. And the lower level here will be this point. That's the lowermost level. Okay. 10 millimeter. So everything is the same. We are close to about 11.3, but that's okay. I'm going to save this. Now we are going to use a feature because this will take some time to calculate. Why? Because first of all, we have a part that's about 500 millimeter long, almost half a meter. So it's going to take some time to calculate. And I don't want to keep you waiting for this. So what we are going to do is we are going to use one of the features available inside SolidCAM, and that is to use the parallel computing power of your CPU. So I'll select both of them and I'll calculate in parallel. I have two options. One, either I can use the local hardware on which I'm currently running SolidCAM, or I could use another computer in the network where we have SolidCAM installed and use its resources to do the calculation for me. Since I'm not in a network at the moment, I'm going to use the local computer and hit the calculation button. What you're seeing here is, sorry, I think I'll have to exit it once and then run it. Okay, I have both the two parts. Let's calculate in parallel. That's strange. Let's reopen. Let's calculate in parallel. This is strange. Okay. We have no option but to calculate it again. Let's have to wait a couple of minutes for it to finish the calculations. What we can do is maybe we can kill the process and start again. Let's hope that it works this time. Okay. That's working fine. So you can see that now it started its calculations, which is running in the background, and the lock key, the symbol indicates that it's being calculated at the moment. But it's actually free for me to do the further calculations while it's running the background calculation. So what I'm going to do is I'm going to now start with my 5-axis calculations, and when we finish that, we will run the simulation. Okay, so we're going to take the first region that's over here, and we'll create some toolpaths for 5-axis. So we're going to use the regular 5-axis engine, morph between two adjacent curves. The geometry, are all these surfaces. Now you'll realize why I split them, because it's much more easier now to create toolpaths if we can segregate them into regions. And then I have the start edge curve. 1, 2, 3. Then you have fourth one, fifth one. Over here, this and this. Okay, that should finish the first one. Yes. And then we have the second curve that we need to select, the end curve. Okay. 1, 2, 3, 4, 5, 6, 7, 8, and this one over here. Okay, this is done. This is my end curve. I'm going to use a 16mm ball nose. 16. Okay, everything is fine, and we're going to have about 40. A 4-flute tool, and the holder is the same, HSK 63. Let's go to the levels. I have cylinder, and that's going to be parallel to X. 125. 10, and then we have 10mm here. Let's go to toolpath parameters, and we'll use a spiral. Tool axis control. We're going to keep it to ISO. Increase the rule surface radius limit. The entry and exits, we're going to use vertical tangent arcs. Okay. Perfect. And the gout check, only the tooltip will be used to check against the drive surfaces. Fine. We've done that. Just save it. You can see that by the time I was defining the 5-axis stuff, we've already it's already done the calculation of the first iMachining toolpath, and the second one is going on. So what I'm going to do is I'm going to put this also in parallel. Okay, and I'm going to run the simulation of the first one. So you can see that the parallel calculations doesn't stop you from working, or it doesn't make you wait. You can keep doing your work while the other things are being calculated or run or simulated. So we have our toolpath out here. can see that it has taken a complete 40 millimeter depth of cut at one go, and then it's using the step-up principle to cut or create the scallops. So that's how the first roughing is going to look like. Okay. The second roughing is still being calculated. Done. The third one is already calculated. What I'm going to do is I'm going to add, or I'm going to simulate in HostCAD. I'm going to see this toolpath because we could make changes, we could do a lot of things to this. The toolpath looks fine, except for the fact that if I go to this point out here, you can see that the tip of the tool is actually doing the cutting. That's because we have given the tilt angle as 0, so the tool is being normal to that surface at every point. Generally, in a ball nose, the tip always has a 0 RPM, so you're actually not really cutting the part or cutting the material. So the best way is to tilt the tool slightly, and to do that, I'll have to again edit this toolpath. Go to the tool axis control and tilt the tool. I'm going to use a 10-degree tilt. We'll hit save and calculate. All this is happening even while the second operation is now being calculated. So we are really not stopping anything. We are not stopping the system. We're not stopping our own toolpath processes. They are all happening simultaneously while we are calculating another toolpath. Okay, so we've done this calculation. Let's see how the toolpath looks like. Toolpath might look okay, but we have some problems out in this area. And this is because of our tilt angle principle. We'll fix that in a moment. Edit this toolpath and use orth to cut at each direction and hit calculate. So this should fix up those strange passes that we got. Okay, it's done. Let's look how the toolpath looks like now. Much better. All those issues are now sorted out. So it's much more clean. And if you run the simulation now, and if you look at the movement of the tool, you can see that the tool is tilted slightly to its left, and instead of the tip cutting, the side of the tool is now cutting the material. So I'm getting a portion of the tool that really has the RPM so that it performs a proper cutting on this particular part. All right, let's go to the next area that we had split up, and we will run the same thing. What I'm going to do is I'm simply going to copy and paste it, and we're going to change the drive and the drive curves and the drive faces. So we have 1, 2, 3, 4, 5, 6, 7. Okay, so these are all the faces that we have. So if I show, these are all the faces that we have just selected. The start edge starts from here. And this is the next one. There's a small surface. I hope I've not missed it. You can always go back, edit, and include that surface. Okay, and the end edge curve now is up here. 1, 2, 3, 4, and 5. That's it. There's nothing else. Let's correct it. Let's go to the tool. It's the same. Toolpath parameters, instead of spiral, it's going to be a zigzag. And let's hit save and calculate. Okay, let's run the simulation. Of course, we have problems here, and that's because of our link. What we're going to do is we're going to go into the link and increase the link between slices value from 110% to 500%, because anything above 500 it's going to take to the clearance plane. Anything less than 500% of the step over, it's going to join using the blend spline option. Okay, let's keep it on and see how the calculation looks like. You can see that that problem is fixed. We have got a nice toolpath now, starting and ending. All right, what remains now is the end one. So again, I'm going to copy the first one and paste it. And the geometry, we'll select the new geometry now. That includes the fillet portion of that surface and the main surfaces themselves. Okay, that's done. Let's select the main contour, first curve. Oops, sorry, that's not the curve, this one. Okay, that's my starting curve. And my end edge curve is out here. Okay. And these are the small bits that will finish it up. Okay. I'm going to use some margins, 0.1 to start, and at the end, to avoid some unforeseen stuff, I'm going to use 0.5 more than the radius of the tool, so that because we have a wall and a fillet, I don't want it to enter into those areas or jump up and down. Say OK. Everything else will remain just the same. Let's calculate. Okay, that's done. Let's look how it looks like. Nice, it's stopping much before, because since I've used a tilt, it's going to stop much before than this wall, and then I've defined sorry, I've defined a margin out there, and the remaining stuff can be done using another tool and a smaller patch of area. Right. Now that we have done the main lobe, we also need to finish the inside, and the inside is going to be done using two different methods. First, we're going to tackle the internal surface. How are we going to do that? We're going to do that using a different method, because let's try the regular one. So I'm going to add Sim 5 axis geometry. I'm going to pick the surface. And the starting curve is up here, and the ending curve is up here. Okay, and let's use the same tool that we used for finishing the envelopes. And we'll use a plane that's parallel to Y. Okay. Zigzag. Okay. Couch check, of course, only with the drive surface. Right, let's save and calculate. Let's see how it looks like. So if I run now the simulation, you can see how the tool will look like. That's obviously it's not going to work. You can see that the tool has now become almost parallel to the rotation axis. This is not going to work. So we need to change the way we tilt the tool, because we have said the tool axis need to be normal to the surface. So theoretically, it's perfectly doing it right because it's normal to that surface at that point. Anyway, because this practically will not work, we need to find another way. Another way is to tilt the tool using a curve. How do we do that? And that's what it's going to work in this situation. Let me go into the part environment, and I'll create an offset of the surface. Let's say about 100 millimeter. Okay, that's the offset. And I'm going to create a face curve of this. I just want one of those pink curves. Okay, and that is going to be my curve for machining. So I'm going to edit this, go into my tool axis control and use tilted to curve, and the curve is this one, and we'll use the tilt type as closest point. Okay. Everything else will remain the same. Let's hit save and calculate. And now if I do the simulation, if I go one by one, you can see that it's much more easier now, because it's the center line of the tool is following the curve. All right. What we'll do is we'll run the machine simulation in this case. Okay. No problem. Ignore those messages. Okay, we also have a problem here, and that is because of my link. So let's correct it. Go into the links. Let's increase the link to 500% again here. Okay, that's done. See that now it's much more smooth. Let's go into the machine simulation. Yes, please. Okay. How is it going to cut? Let's run it slowly. So that's how it's going to run. I just want to see if there are any issues relating to gouges or be going out of limits of the machine. So let's run it very fast. Of course, I'm looking at the machine simulation, and I see that we have a overflow in terms of the B-axis. The B-axis on this machine is designed to go from plus 30 to minus 120. So that's the range, and it's already gone up. You can see out here, it's gone beyond 30. It's gone to 30.144, which is way beyond the limit. So we need to fix the limit. The limit can be fixed in two ways. If you're using a regular tilting type strategy, you can fix it by defining just the limits. For example, if you're using the tilt type as ortho to curve, or tilt type as relative to cutting direction, then you can directly go into the limits, provide the conical limits, and the tool will stay within the conical limits. However, in this case, this is a bit tricky one because we used a curve. In this case, the limits will not just work straightforward. We'll have to do something else. The height of this curve actually determines the basically the angle. How is that? Let me open Paint here. So if I have this face, this wall, face below, and a wall, and I have my curve out here, which is basically here. This distance is, let's say, 100. Now to approach this point, and it has to pass through this, it has to make an angle alpha to reach here, to this point. Now if the same point is taken up further to some other point, let's say at 125, the same angle reduces. You get a different angle now. You don't get the same angle. So the key here is to actually move this particular curve slightly above where it was. So what I'm going to do is I'm going to go to the offset, the surface offset. I'll edit this, and instead of 100, I'll make it 125. Okay. Click OK. Come out. So we're going to have immediately a geometry sync message because it's not trying to sync with the geometry. That's strange. It looks like we need to, okay, let's come out. Right, you can see that it's given me a geometry sync error message, a rebuild, so I can synchronize with the new geometry, and we will recalculate this toolpath. Let's run the simulation again in the machine simulation. Let's cancel. Yes, please. Okay. So we have the toolpath. Let's quickly run to the end and see if we can get the problem. You can see that we did not get any V-axis error because as I move up, the angle starts becoming shorter and shorter. So the distance of that curve is very important if you want to maintain the limits on the machine. So it will exactly machine within the limits provided you are within the range on the height. So you can see that the curve did play a pretty important role. Of course, what we need to do is just to reload this part again because I see a okay. Let's kill the process. It's okay. Let's start SolidWorks back again. Okay, the temporary version. Okay, that was not calculated. So let me put that calculation and let's move ahead. So we have done this calculation, and what now remains is basically these two faces that we need to finish. So I'm going to use it's not calculating, can calculate it later. Let me add a 5-axis parallel to curve. This is the face that I'm going to cut, and the edge curve is up here, and we're going to use single cut using the 16 bull nose, okay, the end mill basically, plane along Y. Toolpath parameters, since it's a single cut, this doesn't much come into play. Okay, I'm going to use the regular side tilt strategy. Tilt is at 90 degree, but I would like to have an extension of 15 millimeters on either side so that I don't directly cut on the stock. Okay, at the gouge check, I'll enable the gouge check, the drive surface, and it's going to be moving the tool away in X positive. I think it's X positive. Oh, it's X negative, sorry. Okay, because it's going to push the tool in negative X if there's a gouge. Okay, let's hit save and calculate. Run the simulation. Because it's going to be like a swarfing kind of a cut, that's how my tool is going to come. And you can see that the tool is now trying to change its orientation as it enters into the job. Go straight and then again change the orientation completely. Now this is not looking nice, because if we go on the machine, we're going to see a lot of dancing or a lot of movement on the C-axis. Cancel this. We'll have a lot of issue with the C-axis. So if you look at the C-axis, or A-axis in this case, we're going to have a lot of dance. You can see that the A-axis out here, on the right-hand side, is changing drastically. So there's a lot of change. It might not give me a good surface finish at the end because there's a lot of C-axis movement or A-axis movement happening. How do we fix this? It's pretty simple fixing this problem, because it's more related to the tilt axis or tilt type basically. So I'm going to change the side tilt definition from orthogonal to cut to orthogonal to cut direction at each contour, and I'm going to use a single vector. That means the vector that is identified at the start of the cut will be kept constant throughout the cut. Let's hit save and calculate. If I go back again to my machine simulation, yes please. Let's have a look again at the C-axis or the A-axis in this case. As I go down step by step, you can see that the A-axis now doesn't change because it's using a single vector. So it's almost like a nice 2.5D cut using swarfing kind of a technique, using the side of the tool. Right, so this finishes that side. Now what remains is the exact other side of this part. So I'm going to save and copy, change the geometry, select this as my face, okay, and the curve, in this case it's going to be this curve. Everything else is the same because I don't change anything else except the geometry. Let's save and calculate. Let's run the simulation. Okay, looks fine. Looks good. Oh, we have a problem here. The problem here is that the tool is trying to dip in because it's no longer getting any surface to hold on. So it's trying to dip into the part. So this is again dangerous for us. We need to change the way this is machined. So this cannot be machined, which means it cannot be machined the same way it was done for this. There's another method, and for that method again we need to do some small preparatory works. First let me hide this fellow here, also this one. I'm going to create an offset of the bottom fillet here. 0. Basically, it makes a copy of that surface. And let me extend or untrim, sorry. Let me untrim that surface and extend it by about 15 millimeters. Both the sides, 15. So that will remove the need for extending the toolpath. Edit. Geometry in this case is going to be this fillet. Edge is this one. And there's no need to do any extend or trim. And the gouge check, it's retracting positive X. Okay, not the drive, but the check surface in this case, because it's no longer a drive surface. Save and calculate. Perfect. Let's look at this result. We have a problem again. The tool is coming from bottom. That's because of that surface normal. So instead of plus 90, I'll make it minus 90. Okay, let's check again the simulation. That's it. It's coming nicely. It's out of that surface, so the entry is outside. And it nicely cuts the surface, the side, with using the side of the tool, leaves the material, climbs out. So rather than sticking on to the surface out there, what we did basically was just to use a bottom surface, the curve, and machine that curve so that it cuts exactly that surface on the side. So it's very important to first of all analyze the part. Second, it's also important to have a good CAD engine next to you so that you can do all this small preparatory works for converting the surface and other things. So in that way, it is pretty useful to have SolidWorks next to you so that all these things can be done easily inside, and then all you need to do is just select those faces. Again, no need to translate them or do any kind of translation. Okay, in the meanwhile, let's calculate this. There seems to be some. Synchronize. Okay, not a big deal. Synchronize. And let's calculate these two first. Okay, we are almost done. If there are any questions, I would be more than glad to answer your questions. So please type them in your chat bar so that I can see those questions. Okay, these two are calculated. Run the calculation for this. Okay, the entire calculation is done. We can now actually run the machine simulation, including the verification enabled. So we have the simulate machine simulation. Yes. Okay, oops, sorry. My mistake. I need to put 250 millimeters as an offset from the Z0 to the center of rotation, and now we can run the machine simulation. No wonder we're getting some errors in y-axis and b-axis also. I have a question here which says that about iMachining, how can we use it here? Will it be useful? Of course. Why I have switched on iMachining in this case is precisely the reason that the roughing can be made much more easier. Now, if you use a regular conventional 3-axis machining, there are several issues that you would encounter. First of all, the parameters itself. What would be your ideal RPM? What would be the roughing feed rate, etc.? What would be the strategy you would use? Would it be good on the tool? Would it be good on the spindle? There are several things, and that is the reason why I have used iMachining. Of course, I have not shown you the semi-finishing operation because that actually doesn't make any sense, because semi-finishing is exactly the replica of finishing, except for the fact that we are going to use some offset that we are going to keep after the semi-finishing operation is done. But iMachining 3D makes sense in this part because, first of all, it cuts down the time. It's good on your tool because your tool life is up. It takes maximum depth of cut. It decides the most optimum cutting conditions for that particular given set of machine, material, holding, and the tool and the geometry. It also facilitates a better cutting, which is much more easier on the machine. So looking at all this, and plus the fact that you're not cutting, of course we are cutting aluminum here, but you're going to cut stainless steel, and stainless steel is not an easy material to cut by any means. And we have seen that with iMachining, the stainless steel cutting is much more better because the kind of parameter it derives, the kind of cutting conditions it calculates is really nice for cutting stainless steel. We've had several of these examples with us with when we have cut with stainless steel. So that's one of the prime reasons why we use iMachining nowadays for most of our roughing work, provided, of course, there's a catch here, provided the part is a moderately small part. I mean, it's not a huge part like you have like 1 meter, 2 meters long part and a deep part, wherein our end mills cannot be used. In such cases, iMachining would not be recommended. iMachining would be recommended in parts up to about 500 millimeter, not 500 by 500, but let's say 500 by 200, or 250 by 250, 300 by 300. We are talking of parts moderate in that size. Complexity is not an issue. The size does become an issue because you're going to use a end mill, solid carbide end mill. And that was one of the reasons what made us use iMachining 3D for this particular part. Of course, The holding in this case on a 100 monoblock is not just by one chuck, but it is by two power chucks on either side. So that is one of the criteria for holding. It's not going to be held on one side by a power chuck and the other side by a tailstock or something, but it's between two power chucks. Another nice thing about the simulation, machine simulation in SolidCAM is, if I don't want to see a particular operation, if I want to directly jump to another operation, I can just select that operation. SolidCAM will immediately start recalculating the exact stock that is going to be there for the next operation. And this is done very fast. You can see we have almost completed 90% of the computation. It's finished, and now it's waiting for the user to start his operations. Now I just have to click on play, and there it starts. And let's say I want to directly jump to the next process. I just select that process. This process will stop, and the next process updation will immediately start. It's very fast in updating the stock within the simulation. You can see in less than 3 or 4 seconds, the stock has been updated for the next operation, and it starts simulating it. Sorry, sorry for that. It was frozen, so I'm going to start again. One moment, let me come out. I'm going to start the simulation again. It was my mistake. I put it on a pause, and then I forgot to start it. So let's run the simulation again for machine simulation. Yes. Okay. What I was trying to tell you that once we start the simulation in iMachining 3D, let's say I've seen for the first 100, 200 blocks, and now I'm no longer interested. I want to jump directly to my 5-axis simulation. In such a case, I can just pause the simulation and click directly the third operation. What SolidCAM will do now is immediately start calculating the stock that is going to be updated for that particular operation. And that's very fast. The calculation is much faster than actual simulation. Sometimes it's very quick. It hardly takes about a few seconds. And you don't have to run through the entire simulation to get to that particular point. You could just click on that on that particular toolpath. The stock is updated and ready for simulation. In this case, it's going to take about 35-40 seconds. Considering the amount of the material that was to be removed and the operations, that's pretty quick. Okay. What it does basically now is it finishes the entire computation of the stock updation, and it gets me to a point where I can now be ready and start the 5-axis simulation. What I could also do is, after I've seen some of these things, I can just click the next operation. You can see how quickly it runs the updation. It will hardly take about 7-8 seconds. The stock updation finishes, and it's now ready to fire the next simulation. So I really don't have to wait for my simulations to finish. Once I'm sure, I can just jump to the next one, just observe what is happening, and finish the simulation in this way. I don't have to really wait for it to calculate the stock and the long process, basically. The simulation inside SolidCAM's machine simulation is fast and quick. Okay, any other questions? I don't see any other questions. You have my email address. So what I'm going to do is I'm going to type my email address in case you want to see any other part, or you have questions about SolidCAM, iMachining 3D, and iMachine and 5-axis. You could send me your questions, and I'll do my best to answer your questions via email. That's my email out here, and I thank you very much for spending your valuable time to have a look at the product, look at iMachining 3D, what it can do, and also simultaneous 5-axis. Thank you very much. Have a nice day.